Annenberg Media.
Water has always been vital to civilization. Cities and towns are usually built along an abundant supply of fresh water, such as a river or a lake. But lakes and rivers can't supply all of the water that we need, so we've tapped into another source, groundwater. The practice of water dowsing, or finding underground water using a forked stick like this one, has been going on for centuries. Typically, the dowser grasps the fork of the stick in each hand and points the other end skyward. Then, as he's walking along and happens to pass over a supply of underground water, the end of the stick, or divining rod, supposedly twists downward, showing where to dig the well. In reality, however, almost anywhere you point the stick, you'd eventually find water. Although its depth varies considerably from place to place, water is present beneath the Earth's surface almost everywhere, even under the driest deserts. Most people tend to take groundwater for granted. But in fact, it's a tremendously valuable resource upon which most of us depend. Over 1/2 of the U.S. population relies on it for its drinking water supply. Even more groundwater is used for irrigating agriculture, and its industrial use is growing every day. Groundwater is valuable because it's plentiful and clean. There's about 50 times more water underground than in all the lakes and rivers on the Earth's surface combined. And in many areas, especially those with dry climates, groundwater is the most abundant and economical source of water available. And because it's filtered as it passes through the soil, groundwater tends to be less polluted than surface water. But this valuable resource is now being threatened. In some places, groundwater has been contaminated by industrial or agricultural pollution. In others, wells are extracting groundwater faster than it can be replenished. Already, this has caused severe economic and health problems in several areas of the world. Consequently, there's an increasingly important role for the geologists who study the movement of water beneath the ground and who can accurately predict the location and quantity of groundwater.
Water, water everywhere, yet not a drop to drink. So went the complaint of the ancient mariner as he looked out over the salty brine. Although the Earth is sometimes referred to as the water planet, only a tiny fraction of this water is usable by human beings. And most of this fresh water comes not from above, but from beneath the Earth's surface. This groundwater originates in various ways. Water percolates continuously into the Earth from lakes and rivers, for example. Most important of all, however, is rainfall. In some places, rainwater readily disappears into the ground. Of course, water doesn't get beneath the land surface with equal ease everywhere on the globe. When it lands on hard bedrock or asphalt pavement, it simply runs off to feed nearby streams and rivers. But if there are cracks or fissures in the surface rock, the water can pass through to collect underground. Even hard rocks, such as basalt or granite, usually have some fractures in them through which water can permeate. Other land surfaces consist of less solid aggregates of material, such as sandstone or sediment or ordinary soil. Here, the water can work its way down through the gaps or interstices between the individual bits of matter. Although permeable rock will let the water through, it still may not be a good source of groundwater. For a rock to contain abundant groundwater, it also needs to have a lot of open spaces, or pores. The capacity to transmit water is called permeability, and the capacity to store water is called porosity. The ideal rock material for the accumulation of groundwater is both porous and permeable. This kind of material is known as an aquifer, from the Latin for water-bearing. Sandstone is a good example of an aquifer. Clay, on the other hand, is a material that tends to exclude the flow of groundwater. It is an aquiclude, the opposite of an aquifer. As clay absorbs liquid, its individual grains swell up while becoming saturated and close the channels between adjoining pores, thus blocking the passage of groundwater. While groundwater has the effect of making clay layers swell, it can eat away other rock types. The most vivid example of this is the formation of caves. Infiltrating groundwater is always slightly acidic because it has reacted with carbon dioxide in the air, thus forming carbonic acid. This acid gradually dissolves limestone, especially along joints. If the groundwater eventually drains off, it will leave behind air-filled caverns. Columns of rock build up inside these caverns. These formations are created by droplets of groundwater seeping into the caves. As each drop clings to the ceiling for a brief moment, enough evaporation takes place to precipitate a minute amount of calcium carbonate. Over centuries, untold millions of such microscopic grains of rock will form stalactites above. And from the buildup of droplets that reach the floor below, stalagmites will form. In places where caves are still flooded, geologists can trace the flow of groundwater by releasing non-toxic dyes that will ultimately reappear at the Earth's surface in the form of springs and rivers. One reason geologists study groundwater is to learn how it moves beneath the Earth's surface. The area in which the water accumulates is known as the saturated zone, and the layer above it, the unsaturated zone. When a well is dug into the saturated zone, the groundwater will fill the lower part of the well. The water level inside the well marks the upper surface of the saturated zone. This surface is called the water table. Where the land surface is flat, the water table beneath it is also flat. But where the land is hilly, the water table will also have an irregular surface, with high and low parts roughly corresponding to the overlying topography. In valleys, the zone of saturation may rise to meet the Earth's surface at river and lake beds. When the rivers and lakes are full, a continuous supply of new groundwater recharges the zone of saturation, and water flows from the surface into the ground. However, during the dry summer months, when surface water levels are low, groundwater may flow in the opposite direction, providing the rivers and lakes with their only supply of water in the absence of rain. This phenomenon is called effluence. Where groundwater flows out through an opening to the surface, as for example along a joint or a fault, springs form. Most springs flow year-round, even through the long, hot months of summer when they might be expected to dry up. This is because the water that comes out of the ground in the summer may well have started its journey the previous winter. Getting water out of the ground requires working against gravity. and pumping the water up. But in some wells, the groundwater will move upward of its own accord, in apparent defiance of gravity. These are called artesian wells. To understand how these valuable wells work, a classification of aquifers into two types, open and closed, is useful. In an open aquifer, a stratum of permeable rock overlies the water table, so that the pressure of the water, in other words, the hydrostatic pressure, at the top of the zone of saturation is quite low, too low for the water to rise up unassisted to the land surface. The other main type of aquifer, the closed aquifer, is overlain by a layer of impermeable rock, an aquiclude. Where such an aquifer is inclined with its highest level exposed at the surface, water can enter directly into it in what is known as the recharge area. The weight of the water entering the inclined aquifer via the recharge area, combined with the confining effect of the layer of impermeable rock above, causes hydrostatic pressure to build up. If a well is dug in the appropriate place, this pressure is often strong enough to drive water up to the surface against the pull of gravity. One way to better understand how hydrostatic pressure can make water flow upward is to try a simple experiment with a hose. When water is poured into the higher end, its weight drives the water up and out the lower end of the hose, even though the lower end is above the sagging middle of the hose. One of the most significant aquifers in the United States lies just south of Los Angeles in Orange County, where it supplies water for 2 million people. The total potential capacity of this aquifer is estimated at between 10 and 30 million acre-feet. This equals the total volume of water that lies beneath the entire state of California. This is all the more surprising because before its settlement, low rainfall made most of this region a virtual desert.
The coastal plain of Southern California, of which Orange County is a part, is particularly well suited for groundwater storage. It has several things going for it. It's very deep, some 4,000 feet deep, to all containing fresh water, of which we only use about the upper 1,500 feet. It has a surface water supply. It's the only perennial stream in Southern California. This stream is fed by snowmelt in a very large mountain range behind us. Again, in a desert area, we have snow that feeds a perennial river system which provides continuous water supply. Another factor that helps out a great deal in maintaining the flow of the water down this river is the fact that we have considerable residential and commercial development upstream of us, which provides us waters of wastewater origin. That means the water has gone through a treatment plant once upstream and has gone through a series of biological cleansing activity, which provides us with a very suitable supply of water to go into our groundwater basin. So we're blessed with very permeable soils, a very large storage capacity, and a steady supply of water.
Part of the success of the Orange County Water District can be traced to measures taken to recharge the local aquifer.
One of the ways the Orange County Water District manages the groundwater basin is by ensuring that we put as much water back into the ground as we take out through a series of extraction wells. This is done primarily through our recharge facilities, much like the one shown in the background here. These recharge basins or facilities consist primarily of old gravel pits and also what's in the channel. The off-channel or old gravel pits capture water from the river and divert it into these basins, where it effectively percolates into the groundwater. All of these basins are underlined by porous, high permeable sediments that are in connection with the underlying aquifers, which effectively extend down into the lower part of the basin. Therefore, water is able to percolate through these basins into the aquifers and effectively recharge the whole Orange County groundwater basin.
Groundwater management requires a great deal of care, not only because the water itself is so vital, but because a diminished supply could cause the ground above to subside, and this, in turn, could trigger a multitude of problems.
As water infiltrates into an aquifer, the permeable rock soaks up the water like a sponge until it's saturated. The weight of this saturated zone generates an aquifer pressure that forces rock particles apart. This pressure also helps to hold up the ground surface, even inflating it slightly. When groundwater is withdrawn, the pressure decreases and the particles pack more tightly together. If the rate of water withdrawal exceeds the rate of infiltration, the overlying ground surface will often subside. Ground subsidence can be dramatic and have disastrous consequences in areas of high groundwater withdrawal. In Houston, Texas, for example, 3 meters of subsidence has occurred over 40 years of overpumping, resulting in tens of millions of dollars of property damage and the loss of 80 square kilometers of land. One suburb, Crystal Cove, had to be abandoned completely because of flooding. In Italy, groundwater withdrawal has caused the lean in the Tower of Pisa and contributes to continued flooding in the canal city of Venice.
Sometimes groundwater withdrawal can cause the ground to collapse, like sand going through the neck of an hourglass, resulting in sinkholes like these. In other regions, the surface of the earth is torn by giant cracks. In coastal regions, the excessive withdrawal of groundwater can cause other problems in addition to subsidence. Beneath land, groundwater is fresh, but underneath the seafloor it is salty. Since fresh water is less dense than seawater, fresh groundwater just inland from the coast will tend to float on top of a saltwater base. If fresh water is pumped out faster than it can be naturally replenished, seawater will flow in to replace it. As a result, the well water becomes increasingly salty, making it useless for drinking and poisonous for irrigation. Other groundwater pollution problems also exist, involving contamination from many sources, such as factories, farms, septic tanks, garbage dumps, and less often, radioactive waste depositories. Headlines like these about toxic drinking water have been all too common in recent years. One way in which we pollute groundwater is through badly designed or improperly maintained landfills. When rain leaches the pollutants from a landfill into the saturated zone, a plume of polluted waste spreads out in the direction of groundwater flow. Fortunately, engineers are now developing more effective techniques to minimize the impact of landfills on groundwater quality. One of the techniques that has been developed recently is a landfill liner system. Its multiple layers act as a barrier between the garbage and the surrounding environment. The base of the liner system is simply a layer of impermeable clay, which is spread around the landfill and compacted by heavy equipment. While the clay itself might be adequate to prevent the seepage of polluted water, or leachate, out of the landfill, extra precautions are taken. A synthetic high-density plastic liner is placed on top of the clay. Next, a half-meter or so of permeable sand, along with drainage pipes, is laid across the plastic. Here, the leachate accumulates and flows out from beneath the landfill for safe disposal elsewhere. At some landfills, the methane gas produced by decaying waste is collected and burned to generate electricity. And so, a composite landfill liner can serve a dual purpose, protecting groundwater quality and providing an additional source of electricity. The great irony about groundwater is how little attention it often gets in discussions about dwindling resources. We worry about running out of oil, and there's no question that it's of great importance to our global economy. But when all is said and done, life could go on even without hydrocarbons. There are, after all, alternative sources of energy. But when it comes to water, there is no substitute. Without water, life is simply not possible. Fortunately, groundwater resources are not as limited or irreplaceable, for groundwater is more rapidly replenished by nature than is oil. But the time scale of natural replenishment is very long, at least by human standards. At the current level of infiltration, it would take thousands of years to restore the water supply that has been pumped from beneath many cities in but a fraction of that time. In addition to ensuring adequate supply, protecting the quality of water is also of utmost importance. Again, Orange County is an excellent example of how geologists go about doing this.
There are two aspects to water quality we have to be concerned about. First of all is we're in a coastal basin. We're next to the ocean. If we draw the basin down, salt water would flow in to take the fresh water's place and thus severely damage the basin. The other aspect is pollution. In the case of saltwater intrusion, we have built injection wells along the coast, and we are either putting imported water in them or we're putting reclaimed wastewater that's produced at our Water Factory 21.
The Orange County injection wells act as a hydraulic barrier along the coast, which keeps the salt water out even if the level of the groundwater in the basin is drastically lowered.
In pollution, we have an industrial base in Orange County and much of Southern California. There is more circuit board manufacturing done per square mile in Orange County than any place else in the world. So we have things that potentially could get into our groundwater basins, solvents, heavy metals, etc. But we have a very detailed source control program that's managed by our sanitation districts here in Orange County that don't allow discharges of that material either into our basins or into the wastewater stream that eventually gets into our injection barrier.
Because water quality is such a vital part of groundwater management, it is essential to monitor the water both above and below the surface.
Traditionally, we've sampled our groundwater basin at the production well, and we still do that because that's the next step is your faucet, and we're very concerned about what reaches the faucet. But it would also be nice to know if there's something coming down the aquifer that we don't know about and find it before it reaches the production well. So what we've done at Orange County is developed a very sophisticated groundwater monitoring program which uses surface water sampling, production well sampling, and dedicated monitoring well sampling. Our monitoring wells are drilled to a depth of about 1,500 feet and isolate and tap up to 18 zones that we can monitor individually so that if a contaminant is coming towards us, towards a production well, we can find it before it becomes a problem and institute a mitigation.
The monitoring wells provide a picture not only of when and where contamination is occurring, but also of the geological structure of the groundwater basin. As a well is drilled, samples of the rock are collected and analyzed. From these data, the substructure is mapped and computer models created to predict how groundwater flows through the basin. This information is extremely important because it helps water district personnel plan how to effectively contain groundwater pollutants.
We don't wait for regulatory agencies such as the state or the EPA to come to us and tell us we've got a problem. It's too late then. So we're looking at managing our own groundwater basin as though we had to drink the water, and we do.
Life demands water, and groundwater is an immensely important natural resource. Groundwater is recharged by the infiltration of rain and snow and surface water into the fractures and pores in rocks. Rocks that are both highly porous and permeable make the best quality aquifers and will contain the most abundant groundwater supplies. Aquifers are vital to the water supplies of both cities and farms, but many are being threatened by problems that need to be addressed now if these aquifers are to be maintained and used by future generations. They are in danger of being depleted, not only by a rapidly rising demand for water, but also by wasteful water use practices. Large-scale land subsidence is a dramatic reminder that the problem of overpumping has been poorly addressed in the past. Aquifers are also in danger of pollution, a problem closely associated with our mounting waste disposal needs and also the increasing toxicity of our waste products. But the groundwater picture is not as bleak as it may seem. In recent years, earth scientists have gained a much clearer view of how aquifers are maintained and the way that water behaves underground. This knowledge is being used to locate new aquifers and to develop strategies for dealing with groundwater-related problems. Some aquifers are being recharged artificially. This protects water quality and prevents subsidence while assuring communities of an adequate water supply. Hydrogeologists using computer models are working to track and predict the movement of groundwater contamination and are actively involved in developing methods for isolating and removing contaminants from the groundwater directly. Although the golden age of hydrogeology is well underway, there's still much work to be done. Hydrogeologists will continue to play a critical role in maintaining the groundwater resources, not only for ourselves, but for future generations.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.